The purpose of this video is to showcase program features while also providing insight to some important technical details. A hypothetical pier model, seen here, is created for the purpose of displaying numerous features. Modeling typically begins by selecting a template model type from the model window, or by retrieving a previously created model. The model is then edited in the user interface, or UI, to create the final desired model configuration. This Analysis Settings window provides the engineer with control over important details regarding the way the model will be processed. These details will be briefly discussed. If linear gross behavior is selected, then the engineer inputs gross parameters, such as overall dimensions, inertia, elastic modulus, and shear modulus, to describe the structural components. For this case, the structural components will be analyzed as linear, and no second-order effects, such as P delta, will be computed. However, soil behavior is always modeled as nonlinear. When a detailed description of the structural members is input, as we shall see later, two options for the analysis are provided: linear and nonlinear. If linear behavior is selected, then FB-MultiPier converts the detailed section property input to gross properties, and a linear analysis is conducted for the structural elements. With this option, biaxial interaction for the structural elements are computed, and a demand capacity is calculated for each element. The linear setting is very useful for preliminary analysis as a model is being built and loads applied. If the model does not converge, then it's likely that the soil has inadequate strength to resist the applied loads. If nonlinear behavior is selected, then the analysis proceeds in such manner as to force the materials to follow their stress-strain paths. Plastic hinging and corresponding force redistribution is possible with this setting. Concrete cracking and corresponding changes in stiffness are automatically taken into account. This setting is useful for conducting a final analysis. The transformed section properties is an input for the linear analysis case where detailed sections have been input. The iteration control is useful to gauge the extent of nonlinear behavior, as the number of iterations needed to reach solution convergence indicate. With some experimentation, a solution tolerance can be selected that provides an acceptable level of accuracy while facilitating a more rapid analysis time, reducing the number of iterations required for convergence of the model. Static dynamic. While static loading is selected for this model, FB-MultiPier is capable of analyzing a pier or bridge model for time history or response spectrum analysis. Here, modeling of advanced behaviors such as material hysteresis and dynamic soil structure interaction are available. The engineer may uncheck the Include Soil box. The program will then remove the soil from the model and apply stiff springs at the pile tips, basically fixing the pile tips. This option may be useful in checking a model, especially in linear analysis mode. The coupled axial and lateral soil resistance, when checked, will automatically generate moment resistance that is coupled with axial skin friction acting on the pile or shaft surface. This feature is typically used for large diameter drilled shafts founded in relatively stiff soils. A user-defined phi factor may be supplied by the engineer and will be applied uniformly to the member capacity. Otherwise, AASHTO phi factors will be utilized in computing the biaxial load-moment interaction envelope, which is integral to the program's calculation of demand capacity ratios for design. A value of phi equals 1 is often used for extreme event cases. If the AASHTO box is checked, then FB-MultiPier will allow for creation of AASHTO load combinations, as will be seen shortly. The stiffness option allows the engineer to obtain a 6x6 stiffness matrix at any selected node in the model. This matrix is then computed and printed for each load case and represents the stiffness of the model with all loads in the case applied. This option may be used as input to other software packages. Clicking Coordinate System allows one to modify the default FB-MultiPier coordinate system. The print control simply allows for the customization of the text output file. The AASHTO feature allows for the automated generation of load limit states as seen here. The load case manager is used to drag the pertinent load types into the defined load case window. As these loads are selected, FB-MultiPier automatically facilitates the input of data, as can be seen on the load page. Next, limit states are selected by checking the appropriate boxes as seen here. If a limit state is checked for which a load case is missing, then the program alerts the user to this situation. Edit Load Factors allows the engineer to preview the load factors that FB-MultiPier will use. These load factors can be edited, which provides a powerful tool to create customized load cases. At this time, clicking on Preview Load Combinations allows for an overview of the current load combinations that will be processed. The wind generator allows for up to 5 wind angles. The wind pressures can be viewed and also edited in the wind pressures table. The wind forces are resolved at nodes located on the pier cap center line between bearings and automatically populate the wind on structure and wind on live load cases. The wind generator does not supply the magnitude of the vertical wind, but the engineer may select a node and enter it manually. Under lateral stability, there are 2 options: pushover analysis and minimum pile tip embedment. We will demonstrate the minimum pile embedment feature now. For this model, we have AASHTO Extreme 2 CV selected. FB-MultiPier will conduct a minimum pile tip embedment analysis for each load combination while incrementing the pile length to iteratively reduced lengths. Typically, soil tip resistance is selected to prevent axial failure up to required ultimate capacity. Once the analysis is complete, one may view plots of the pile head displacement versus pile embedment via the design tables. The pier columns are located at the center of the pile cap along the x-axis. The columns are attached via rigid links generated by FB-MultiPier. Pile cap elements can be removed to create desired shapes, and the elements can easily be modified with regard to weight, stiffness, and thickness. This feature allows for convenient stiffening at concentrated column locations. At this time, we'll reopen our original model to inspect the piles. Piles may be selected from a stored library of piles, or a customized pile may be entered. In this case, a drilled shaft with and without casing and full properties has been input. Properties for mild steel, concrete, and casing are input, and FB-MultiPier automatically generates the stress-strain curves as seen here. The engineer also has the option of inputting user-defined stress-strain curves. Fixed or pinned pile head connections can be selected, or any fixity condition can be established through selection of the pile section at the head. Soil. There are three basic soil types: cohesionless, cohesive, and rock. FB-MultiPier prompts the engineer for the soil parameter input, which is then used by FB-MultiPier to produce the nonlinear springs. These springs are applied to each pile node and control the soil response to lateral, axial, and torsional pile forces. User-defined soil resistance curves can also be input. The plot button allows for the visualization of the various soil support curves. The group feature allows for the lateral and vertical group behavior. Lead and trailing row directions for the PY curves are automatically assigned for each load case based on the foundation displacement. Soil data may also be conveniently imported or exported to other FB-MultiPier files, and the cyclic loading option can be utilized when appropriate. The pier page. These windows allow for the input of columns and pier cap data. For this case, we've generated 40 bars with an area of 1.56 square inches at a group diameter of 88 inches. Any number of bar groups can be generated. This column is tapered from 100-inch diameter at the base to 66-inch diameter at the top. The cover concrete is maintained while the reinforcement follows the taper slope to column top. The pier cap is comprised of tapered rectangular reinforced sections. It's possible to input any reinforcement configuration into the section. Extra members. FB-MultiPier allows the engineer to conveniently apply beam elements to the pier or foundation. These beams have two nodes, one on each end, and the engineer has the flexibility to select the end restraint conditions as pinned or fixed. These members can be used as struts or to overlay another member to add stiffness, or as a cross bracing between columns or piles. The sections available are the same as those available for piles, columns, or pier caps. In this case, we have input a bullet shape. Loads. In this case, wind on structure and wind on live load were generated by FB-MultiPier as previously discussed under the AASHTO heading. The other loads are input by the engineer as bearing loads, or one may apply forces to any nodes in the model. The distributed load feature may be used to generate loads on a member. In this case, we've generated a linear distributed load on pile 4 under Loading WA, water loads. The self-weight of the substructure unit is automatically computed based on the unit weights assigned and is incorporated in the DC case. Buoyancy is also automatically included in the water load case. The AASHTO load table also allows for convenient editing and management of loads. Springs. Springs may be applied to any node on the pier or piles. In this case, an X-direction spring with a stiffness of 100 kips per inch was applied to node 272 in the pier cap. Springs applied in this manner are linear elastic. Next, we will briefly demonstrate how a bridge model can be created. In this case, we will begin with the already completed single pier model. A single span is established utilizing the already completed single pier model. Default superstructure properties are assigned which can be edited. Bridge page. The bridge models are extremely useful for determining load distribution to the individual piers, as well as applications such as vessel collision design and dynamic analysis. Additional substructure units can be added by simply selecting a pier or pile bent from the current model, or any other previously developed pier or bent model. When two rows of bearings are defined at a pier, as in this model's Pier 2, one may check the continuous span at substructure box to create continuity at interior piers. A useful feature for modeling bridges is the ability to include linear or nonlinear stiffnesses of bearings. In this case, bearings are restrained in the X or transverse direction. For Y translations in the bearings, a custom-defined number 6 stopgap bearing is indicated. Z direction or vertical movement is restrained and all rotations are released or free to rotate. The span copy feature may be used to copy span properties from one span to any other span. When span longitudinal symmetry is present, span properties can be mirrored from one span to another. Span section properties can be input defining the superstructure section and allowing for automated computation of self-weight and elastic section properties used for both stiffness and temperature force effects. On the bridge span properties page, the span profile information is used for the wind load generation feature, allowing for wind on live load and wind on structure. FB-MultiPier makes use of a spine model approach to account for the superstructure deck and girders. The transfer beam and vertical link are elastic beam elements, which are used to connect the superstructure spine model portions to the bearings atop each pier or bent. FB-MultiPier automatically assigns properties for these intermediate superstructure elements. Or, if desired, the engineer has the option of customizing transfer beam and vertical link properties. Further, the engineer has the option of allowing the program to automatically adjust the behaviors of the intermediate superstructure elements so that span self-weight is distributed uniformly to the bearings. Next, we will focus on the FB-MultiPier analysis results side of the software. Piyo Results. Pile force, displacement, and soil reactions are displayed graphically. This feature is very useful, especially during the iterative design process, as pile layout and pile sizes are being determined. As an example, we'll display M3, V2, axial, and DC windows. Selecting max and min for all forces across all load combinations, we can now see results graphically and additional numerical details above. Piyo Results. As with the Piyo Results, the engineer has the flexibility to quickly interrogate pertinent analysis Piyo results. For this case, we will select max DC ratio for limit state and select column number 2 to view the DC for this column for various limit states. The pier cap forces may also be viewed in a similar manner. Piyo interaction. Biaxial and uniaxial strength interactions are calculated and utilized by FB-MultiPier when reporting the demand capacity ratios. The engineer may view interaction diagrams with selected element end forces, I and J nodes, projected upon the diagram. FB-MultiPier automatically selects the appropriate section of the interaction diagram to view based upon the signs and direction of M2 and M3 moments. The pile number and pile segment are identified along with the element number. Right-clicking the window allows for convenient options when viewing or saving the interaction diagram data. Pier interaction. As with the pile interaction option, we can view similar features for the pier cap and columns. For the pier cap, bending occurs primarily about the local 3-axis, as evidenced by viewing the interaction diagram. "3D results." This window allows for both graphic and numerical displays of any selected load case or combination. Viewing the display structure is helpful in confirming proper behavior. Contours of stress and displacement are available for the pile cap. Right-clicking the 3D window brings up a context menu from which a multitude of display options are available. The node selection option allows for viewing any node, and its displacement and coordinates are displayed in the 3D display control. Selecting element forces allows one to study all pertinent data for that element. Selecting pile cap force plot enables the engineer to view cap forces across selected sections of the pile cap. These are numerically integrated results from the shell element stresses. XML reporting. This feature is available for engineers who wish to create customized reports for their clients. Printing data to an XML file is enabled in the Print Control section of the Analysis Settings page. While engineers are welcome to develop in-house tools for post-processing XML data, a browser-based report generator is packaged along with FB-MultiPier. Note that the XML Report Generator makes use of Microsoft ActiveX controls. The XML Report Generator consists of two browser tabs, a menu where the customized data report components can be selected, and the customized report itself. For example, if summary prints of pile strains and corresponding stresses are of interest, then only that content would be included in the custom report, and the controlling strains could be quickly identified. Design tables. The design tables are available in Excel, PDF, and text format. These tables have been designed to report FB-MultiPier results in a convenient format. Plots of the pier cap envelopes are also available to assist in the design of the pier cap. This ends the current video, where we hope that engineers have gained a better understanding of modeling and analysis results viewing features that are available in FB-MultiPier. Thanks for watching.